Hi, everybody. Hope you had a great spring break. It's Easter for me. Hope you had a good Easter. Mine was pretty nice. A lot of it home, but cool stuff. Easter presents for the kiddos. And generally a pretty good day. There we go. Blowing bubbles. This is pretty cool. I don't think you can see it, but I can see it. And there's a reflection of my shirt, but it's upside down. And if you're curious, you might wonder why. And we'll talk about that soon when we cover optics. But first, we need to cover waves, and that's going to happen at the end of this week. So I'm excited to start that unit, and hopefully you are too. For this week, we're going to finish machines. On Tuesday, we'll have a quiz. The study topics are on page 277. You're actually staring at them right now. They are right here. And we will have a review on Wednesday. I'll have a little Zoom from 11 to 11:30. And I'll also make a video much like this one that covers all the topics we talk about in the review. Let's see. So, like I said, I think I said this, quiz Tuesday. On Friday, we'll have an exam on machines. It'll be due on Sunday, so you'll have some flex time in which to get it done. So this is today, Monday. We've got quiz on Tuesday. I'll give you a few practice problems on Tuesday as well. Review on Wednesday. Again, a couple more practice questions and problems and such. Thursday, we're going to start waves. Friday, we'll have the exam available, and then the next week, more waves. Okay, so that's schedule stuff. I did want to talk a little bit about distance learning. We've actually covered this before. I made this an assignment a while back. Right here. Hello. There we go. How to learn from a flipped educational video. We watched this in class. And I won't play it now, but I'm going to put a link in the agenda for today. And it would be good to revisit this, especially if you're struggling with learning at home. Because it takes a different setting and level of focus. And some of these things may be easy to come by in your house, and some of them may not. So you may need to be creative with how you figure this stuff out. But this is a good one to watch to give you some stuff to think about for how to make this last couple months in school be beneficial for you. Okay, so that's our first thing. All right, so let's go over the lesson for today. It's on machines. And so here we go. Move myself a little bit out of the way here. So what's the purpose of a machine? This basically what's here is what we were working on with the Rube Goldberg machine. You were making a machine that was a bit silly in the fact that it was very complex, but the goal was for you to connect machines, understand machines, and see how we use machines to do work. Machines. This is your warm-up for today. Can a machine make a task require less work? So think about that for a second, or a few seconds. Can a machine make a task require less work? If yes, say how. If no, say why not. So pause the video now and answer that question. Did you pause? If you didn't pause. Okay. So, if you said yes, what would that mean? If a machine could change the amount of work done, first let's actually think about what is work. So remember, work here is the transfer of energy by mechanical means. So if you got hung up there, you didn't know what work was, there it is. If you still haven't answered this question, do it now. Do it. Okay, no more pausing. Here we go for real. So, machines, if you said that, yes, a machine could make a task require less work, that would mean that, say, you could put 10 joules of energy in and get 15 joules of energy out. Does that make sense? We always say that energy is conserved, and so to put more in or to put less in and get more out wouldn't make sense. That'd be that energy was just magically appearing from somewhere. If that was the case, we'd have free energy, no more global energy crisis, no more global warming. Everything would be gravy. But that's not the case, unless there's a conspiracy. 5G, who knows? Anyway, so if no, why not? Well, this is the answer. We talk about a bicycle. A bicycle has gears on it. Actually, I'm getting ahead of myself. So if no, why not? Well, efficiency. All right, efficiency. You have losses from efficiency. Whatever energy you put in, you don't get all of it out. So here's where I'll talk about a bicycle. When you're riding a bike, what's that stuff that's hitting you in the face all the time, especially when you're going really fast? That stuff, right? Wind. So that's a big loss in efficiency there. That's from friction. There's also friction in other places. Like, I don't have a bike gear in front of me, but this is a hinge, and there's hinges in between each piece of the chain that goes from the front gear to the rear gear. And those hinges on each that connect each individual gear have to move. And I don't know if you'll be able to hear this, but right, as I'm moving this, it's making sound, which means there's rubbing going on, which means there's friction. And that means that there are efficiency losses. So machines aren't perfect. But what do machines do for us? Well, this is a great machine, right? Much like a nutcracker or any other kind of lever that gives you mechanical advantage. I could put something in here, and with my hands, could I squeeze a lemon or a lime, which is what this is for? Sure. Yeah, I could do that. But it's way easier to do it with this, and I get a lot more juice out, right? And the further out I hold my hand, right, if I get out here versus in here, I get more advantage. So that's the point of machines. They just make things easier or make things work better in one way or another. Okay, moving on. Okay, so the assignment for today is to do this How It Works classwork. It's right over here. So I will move myself back on over to this side. There I go. And this is all about bike gear shifters. So in a multi-speed bicycle with 2 or 3 front gears and 5 to 8 rear, this actually goes up to about 10 now, rear gears, the front and rear derailleurs or shifters are employed to position the chain, and changing the combination of front and rear gears varies the ideal mechanical advantage of the system. A larger ideal mechanical advantage reduces effort in climbing hills. A lower ideal mechanical advantage allows for greater speed on level ground, but more effort is required. So this is like a force reducer, right? You have to put in more force to get the bike to accelerate, but it's a distance increaser, and the other way around for climbing hills. So you can look at all of the different parts of the bike and see what each piece does. And then we've got some questions down here. So the first question you're asked to think about is, what's the IMA of a multi-speed bicycle in the following 2 instances? We've got one with 52 teeth on the front gear, right? So that's here, and 14 on the rear. And then another one with 42 teeth and 34 teeth. And then we're supposed to follow that up by saying, which of these would you select to race with a friend on level ground? And so level ground, right, flat. And which would you use to climb a steep hill, right? So let's think about that. So if we're supposed to calculate IMA, then these are our givens, right? We've got the front and the rear teeth. We know the equation for IMA, and if you aren't familiar with it, it's all here in the review section. This is it: distance for the effort, and then distance for the resistance. This is also the input and the output, and I've written that here. So basically, it's the input divided by the output. That's the ideal mechanical advantage. For a bike, we actually have a few different inputs and a few different outputs. So where's our first input? All right, this is our equation. Let's figure this out. Where's our first input on a bike? What do you do to get it moving? Okay, you push on the pedal. So that means you're pushing down on the pedal. So that's your input. And so that would be here, the pedal arm. And we're going to divide that by the output there. The output there is going to be related to this gear on the front. So that's down here in the denominator. And then that force here is going to be translated back here to the rear gear. So the next input, right, the output is the input here on the back wheel. That input is going to be the number of teeth on the rear gear. And that's going to be translated to be output here on the rear wheel. Excuse me, the rear tire, right, the rubber part. And so that goes down here. So those are the four parts when dealing with a bike. So for this, when we're trying to figure out the change in IMA and what's different between those two sets of gear teeth, we're really only changing two things. So we need to consider those things that are changing. We can ignore two of the four parts in the above equation. So which of these two things stays the same? And again, remember, we're shifting gears. So which of these two stays the same? If we're shifting gears, the teeth aren't going to stay the same, but what will stay the same is it's the same bike, right? So if the bike's the same, it's not like you're changing where the pedals are or how big the tire in the back is. Those parts stay the same. So these two things stay the same. The only thing that changes is that these two pieces of information here. So that's all we have to consider. I think I hid them right here. Oh, yeah, I did. Doo-doo. There we go. Okay, so we just need to consider these two parts, the number of teeth on the rear gear divided by the number of teeth on the front gear. So that means 14 divided by 52. And if I put that up here, 14 divided by 52, it is 0.269. How many sig figs do I get? 2. Which means it's 0.27. Okay, so what does that mean? 0.27. That means that for every one time that the rear gear and the rear wheel makes one revolution, the front gear, and therefore the front pedal, remember those things are locked together, makes 0.27 revolutions. This is almost a 4-to-1 ratio. If you take the inverse, you'll see that for every one revolution of the pedals, right, your foot goes around once, you get 3.7 revolutions of the wheel, which is much bigger. That's a really huge distance multiplier. This is why bikes get us so far so fast without our feet doing a whole lot of movement, and why they're such efficient machines. Pretty amazing things. Okay, so there we go. That's a big distance multiplier. You do have to push pretty hard, though. Think about being in a high gear on a bicycle. You really got to push hard to get that pedal to go around. Okay, let's look at the other scenario here. Oop, I forgot to change this. So let's look at the problem again, make sure I get it right. We had 42 teeth in the front and 34 in the back. So 42... 34. Okay, so there's our IMA. This time it's not such a big distance multiplier. This is going to be more of a force. It's not a force multiplier, but it's close to that. This is close to a 1-to-1 ratio. And let's look what the math is there. 34 divided by 42 is 0.809. So 0.809, which we would round to 0.81 because it's, again, 2 sig figs. So this is 0.81. And so this is not a big distance multiplier, but what it is instead is a kind of a force not reducer. This means that you're going to be spinning the front pedals quite a bit just to get the back wheel to go around a little bit more than once. But it makes it a lot easier. You don't have to push as hard. And you've probably, hopefully, experienced this riding bikes. Okay, so the next question. What do you want to do if you're racing? Do you want to do a distance multiplied in exchange for force reduction, or do you want to do distance reduced in exchange for force increased? What are you trying to do here? If you're racing, are you trying to go farther, faster, or are you trying to make each pedal revolution with your feet easier? Right? When you're racing, you're willing to be able to have to push really hard in order to go far with each revolution of the pedals, which equates to going fast. So the answer there was you would want this scenario. You'd want scenario A. For climbing, what would you want? Would you want distance multiplied in exchange for force reduction? Or would you want distance reduced in exchange for increased force? In this case, you want to not go as far, but to have it be easier to not go as far. So when you go into this kind of gear ratio here with the 42 to 34, which is close to a 1-to-1 ratio, now you're talking about each pedal stroke being relatively easy. Right? You're not going very far. Right? You're trading distance for ease of effort versus the racing one, you're trading a big effort for more distance. So that's IMA as it applies to bicycles, which is a pretty neat thing. And that's it for today. I will post a quiz and it'll be available, and I'll send out a message when I do that. And if you have any questions, let me know. Send me a message on the Ryan app. Hope you're doing well. Last thing, we'll close it like this. Whose house? Your house. Stay home.